Hi folks, back again, and hopefully this will be one of the last times that we'll be doing this. It feels a bit strange recording these videos now that I'm spending most of my time back in school, but for the complications of having so few of you in at any one time, we're going to be doing this at least for the next few weeks. So this is going to be an introduction to space physics, and I'm going to explain a little bit about what I think you should have done, and what we're going to do, or what you're going to do over the next few weeks. Now, you may remember back in would have been the first lockdown, you would have finished radiation. You would have still been in S3 at this time, but you finished radiation, and we gave you a topic, and it was called S3 space. And to find that, you should still be enrolled in this classroom, so S4 Physics for TROS. And if you're clicking in there, the easiest way to find all of the materials would be in the classwork tab. So looking in classwork, these are the assignments that we set, and the first one that you can look at is this S3 space here. We have a Google Doc. There's answers to the questions that are contained within this booklet. Now, if we look at this booklet, what we'll see is that this is pretty much was taken directly from the National 5 space booklet, which incidentally it's in the course notes folder. So if you're looking in Classroom National 5 Physics Resources course notes, and this is the same booklet that you should have a paper copy of. You'll see, if we're comparing the two documents, then they're going to be almost exactly the same, page for page the same. So you've done most of this already, and in fact when I compared the two booklets, it was only, I think, 3 things which we didn't really get into in S3 space, just due to the level of complexity. But what I'm going to do is I'm going to go through it all. Just some I'll spend more time going over than other bits, and we'll sort of match up there. The good thing about this S3 space booklet is that it does have questions in it, and it probably has more in-depth questions. For example, you have stuff on satellite orbits. Some of these are great, some are less useful. Certainly if we're looking at the space problem booklet here that you would have, this is just the one that we find in Google Drive. The questions are quite limited. There's not that many of them, and I may decide that I'll combine both of them into a sort of more ordered problem booklet. If I don't do that, I've yet to decide that. But if I don't do that, I'll direct you to specific problems to do as we're going through this. As I say, I expect that this will take us 3 weeks to do. Well, 2 weeks and whatever's left of this week. It's been difficult for me to get time to be here to record. I've been in school pretty much most of the time since the start of the week. So I'll try and get what I can done. I'll try and do what I can when I can. But certainly by the end of this term, we'll have covered all of space. Okay, so let's get started, and the first thing that I guess we'll do is we'll go and look at the learning outcomes and see what we're actually going to be doing in this. So we're going to chapter 7, I guess, space and space exploration. So I have a basic understanding of the universe, and I'll come back to that. I'm not going to do this in the correct order here. The basic understanding of the universe will come at the end when we're talking about Big Bang Theory and all of these things. But we're starting off, I can use the following terms correctly, and in context: planet, dwarf planet, moon, sun, asteroid, solar system, star, exoplanet. You'll find this in both books. It's the first thing that we look at. It gives you basic definitions of them. That in the course notes as well. What I would say is that really, if you're going to have a good understanding of what a star is, what a planet is, what a moon is, and then the universe, a solar system, galaxy. And so sort of going from that, the universe contains everything. Within the universe you'll have individual galaxies. Galaxies will contain billions of stars. They're thought to have a black hole at the centre, certainly of most galaxies, if not all galaxies, and there'll be billions of stars orbiting around this galactic core. Each star will potentially have a solar system. Until a few years ago, I would say a few years ago, we weren't sure whether stars existed in isolation or whether, like ours, we had a series of planets that were orbiting stars. And as we discover more what we're going to call exoplanets, as we discover more exoplanets around stars, we certainly, our current understanding is that it's the most common thing for a star to have planetary systems around it, and we would call that a solar system. So the set of objects in orbit around a star, that obviously contains planets. Planets are there's a pretty detailed explanation there, but generally a planet is a spherical object that's orbiting a star that is not undergoing nuclear fusion. From that we would then have moons. So a moon is a natural satellite. Here we've got satellite. It says a natural object orbiting a planet. What I would probably say, and here I'm going to just change this, and you can see me change this right here. I would probably be calling that a moon. So a moon is a natural satellite that orbits a planet. We obviously have, I'm not going to say unnatural satellites, but man-made satellites. In definition of celestial objects, move on. Have a basic understanding of that. Now, benefits of space exploration. Well, let's go back to the learning intentions and where are the benefits of satellites. For example, GPS, weather forecasting, communications, blah, 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 blah. Okay, now, satellites, with this we'll deal with two things. So first of all, what benefits have exploring space brought to humankind? And if we're looking here, benefits of space exploration, well, there's a bit in satellites there, but then we have this space technology. And there's a page here, there's lots of writing. I wouldn't really pay too much attention to this. What I want you to do in your task for this is just to remember one or two things, that have a read through it all and just read and say, oh wow, infrared thermometers, whatever it is, pick one. So a powdered non-liquid lubricant, PS300. Could I use that on my bike? That interests me. So pick something that you're going to remember. Remember one, possibly two things, and move on from there. I don't expect you to be able to recite a big list of benefits of spin-off technologies that have come from space exploration. It's just simply not needed. Remember one thing, maybe two, move on. Satellites, well, again, that there's lots of things that satellites have done, and we can keep going through here. I would pick two, and if you're asked to describe how satellites have benefited us, well, I would say that the two most common ones, and that is GPS. And I'm sure everybody will use GPS at some point. You can use it for sat-nav, and it's an incredibly useful thing in our everyday lives. The other thing would be weather forecasting. And if you imagine, well, hang on a second. So before the advent of satellites and weather forecasting using satellites, we would essentially, we would go out of our house, we'd look up in the sky and it's like, it's sunny, yeah, okay, right, it's going to be a nice day. And that was the basic extent of our understanding of weather. What we could do is we could look at the cloud and say the cloud is blowing at this direction, and if it's blowing in 15 miles an hour in that direction, then we know in an hour, whatever weather 15 miles away, we're going to have that in an hour's time. And so that's what the weather is going to be like in an hour's time, because the atmosphere is moving, and the weather is basically is formed by whatever is in the atmosphere above us at any one time. Wind strengths will be determined by moving air currents, and so as the air rises, it pushes air out of the way, which will determine the winds and everything else. The amount of precipitation that we have, the rain that we have, is all to do with the movement of air currents. We could also send up a weather balloon, so we get this helium balloon. We can send up this, and we can measure things like air pressure. We can find out the temperature in the ground and the temperature up here, and then we can build models to know that if the hot air is rising at a certain speed, and we could do all of this. And so we could weather forecast before satellites, and it was okay, but it just wasn't that great. You know, we could have a fairly good idea of 24 hours in advance to see our weather. But if you're now thinking about looking down, so you take a satellite and you're looking down on the Earth as this is, and well, if we're just going to have a very quick, I know you'll just all moan and whine at me about here, this is not quite right. And it's not quite right, but there we go. There's the world. As a very quick sketch. Now, and so if we have a satellite and we're looking down on this, and we can get sort of a global view of this, and so rather than having an individual cloud as we would here, we could have a weather system. So this weather system is formed over the Atlantic, and we have a much greater range of view, and so we can see this weather system is moving. We have a lot of our weather comes from the prevailing southwest winds, and so coming off the Atlantic, it'll come from the south and the west, and it'll move up through here. And so from this we can see how quickly these massive, I mean these are sort of the size of the Atlantic Ocean, how quickly these weather systems are moving. And this is going to be coming here. We can have another weather system which is going to be moving around like this. And so we can forecast with much greater accuracy and for a much longer period of time. And so there's a couple of things that we have for uses of satellites. GPS, obviously, as a very basic GPS, we'll have some satellites. Satellites will be able to, the satellites that are orbiting, they'll know their position at any given moment in time. And you're standing somewhere, let's say you're on holiday in India, and you want to know exactly where you are. Well, your mobile phone can send a signal up to one satellite, and it can time how long it takes to get there. And then there'll be another satellite that you'll have in your range, and it knows how long it takes to get there. And you may have heard of a term called triangulating your position. And so just by doing some pretty rudimentary speed, distance, time calculations, it'll time how long it takes for the signals to get to the satellites, and from that point you will be able to pinpoint your location. If you have a triangle formed, there will only be one place that you can be, because the satellites will know, if it knows this length, and this length, you can accurately identify exactly where you are. Okay, so that's the first things, the very start of space physics. We're going to be able to know what is out there in terms of planets and stars, And we've got some benefits and some uses of why we bother with space at all. Now, we can see from here that we have geostationary satellites, and geostationary satellites is one of the things that we didn't really touch in the S3 booklet. And while we mentioned satellites and we mentioned their uses, we didn't really talk about what a satellite was specifically in terms of how it gets there in the first place, how it stays there. I know in Dynamics unit I did a lesson about satellites and about how to launch satellites, and so I'm gonna recap about satellites now that we've gone through all of Dynamics and we're starting space. I'm gonna kind of do a bit of a rehash of that and just go over that again. And this will take us geostationary satellites, and then we're talking about period of satellites. And so, right, so we'll get started with that. Okay, so satellite motion. First of all, what is a satellite? Well, if we start off with our planet Earth, the biggie, then we can have a satellite, and our satellite will be orbiting. Now, the satellite will be following a projectile motion path. How it gets up there, we're going to specifically go back and look at launching of space rockets, and which 90% of the stuff that gets launched up into space currently is to put satellites up in orbit. There'll be an interesting in the next few years. Space Scotland is about to take off. There's a couple of potential sites. There's one in Moray, where they're actually going to build the rockets and the engines to launch these special satellites. They're called CubeSats, and they're tiny. The satellites, you think of a satellite as being a really, really big thing, but Scotland is one of the leading producers of these very small CubeSats, and they're this big. I mean, really are very small. And there's a couple of projected launch areas. One is up in Caithness, and there's one up in the Western Isles. And so, hopefully, in the next few years, then satellite launches from Scotland will be a common occurrence, and certainly is a awe-inspiring thing to see a space rocket take off from the surface of the Earth. It's the power that is evident in order to get this thing into orbit is pretty impressive. So I would certainly recommend, if you ever get a chance, go and see a satellite launch or go and see a space rocket launch off. It's awesome. So I'll talk more about the physics involved in launching rockets in a later section when we're focusing on Newton's laws and things. But really, once the satellite's already up there, so we have our satellite here, and we're going to have it moving in an orbit. Now, the orbit of a satellite is characterized by two things. The first thing is it has a constant horizontal velocity. We can call this VH. And it will also have constant acceleration. And it's going to accelerate down. Now the acceleration that it goes down with will be determined by its altitude above the Earth. In a little while I'll show you a graph about how the gravity will vary at different altitudes. But needless to say, a satellite can maintain a stable orbit just by having the right amount of horizontal velocity. So what is happening as the satellite is moving horizontally, it's also falling down. And as it's falling down, it's going to move down a wee bit, it's going to move along and down a wee bit. And if the horizontal velocity is not big enough, then it's not going to be able to move far enough along, and it will eventually crash into the Earth. But if the horizontal velocity is just right, then as it falls, it will fall exactly around the curvature of the Earth. Okay, and we've got to get our heads around the fact that gravity, we think gravity is just acting down, and if we're looking at a page here, then this is the down way here, but actually gravity is going to be wherever it points to the center of the Earth. So if it's here, by the time it's here, it's just going to keep doing exactly the same thing. It's just going to keep falling down towards the center of the Earth. And it's going to keep curving round in this stable path. And so the satellite is going to keep moving around. It can achieve this constant horizontal velocity, not because there is no gravity in space. There you go. I hope that makes it clear. There is gravity in space. Now, I'm not saying that you cannot go anywhere in the universe, in the galaxy, the universe, or wherever, where you will find no gravity. That's not what I'm saying. You can go to places where there is minimal amounts of gravity. You can go to places where there is strong gravity. But generally, if we're talking about satellites, we are going to say that there is gravity there. The only reason that a satellite can be in orbit around our Earth is due to gravity, because this constant acceleration is produced by the gravitational attraction to the planet. The reason a satellite can stay in motion is because space is a vacuum. Because space is a vacuum, if the rocket, if the spacecraft, the satellite is traveling, then there is going to be no forces acting on it. There's going to be no friction because there's no air. Friction is caused by the air, among other things. And so if it's moving through the air, Newton's first law will apply. An object will remain at rest or a constant velocity unless acted upon by an unbalanced force. And there is no other forces, certainly there's no horizontal forces acting on the satellite to make it change its horizontal velocity. There is a gravitational force acting downwards, so it acts what we would say perpendicular to its motion. If it's moving like that, there's a force that's acting perpendicular to its motion, and therefore that does cause a change in its motion. That's what causes the curved path. So because it's moving in a curved path, this is caused by the gravity, the acceleration caused by the gravity. But the horizontal velocity is constant because there is no atmosphere in space once you get up above the atmosphere. Okay. Now, gravity in space. Let's go and have a look at this. Okay, here's a okay, yeah. Oh dear. Right. So what I've done is I've done just a little graph, and it is the numbers are pretty full on, but what we have is we have the gravitational field strength, and so up here 9.8, and here is 0. So this is at sea level. So at a height of 0 meters above the Earth's surface, we can see that the gravity is 9.8. And sure, as you get higher and higher and higher, gravity decreases. But to put this in context, this is in thousands of kilometers. So that's 1,000 kilometer. If you go to the top of Mount Everest, which is around about 8 kilometers from sea level, well, you have to go, that's 100 kilometers, and so you have to go into 8, well, if you divide that into 100, you'll go up to 8 there. So although gravity will be less than the top of Mount Everest, it decreases by such a fractional amount that it's negligible. ISS, well, first of all, the atmosphere. So the atmosphere, the edge of the Earth's atmosphere, so what we would classify as being space, is right here. So see if I was to... let's go. Right, so I'm gonna, let's see, insert, I'm gonna do an arrow now. There. That is the edge of space, right about there. So we're looking at the atmosphere extends for 100 kilometers above sea level, and then there's nothing. That's where we would have the sort of cutoff point of being in space. Let's go for this. The International Space Station, where the astronauts are all going floaty floaty, we would have that about 1, 2, 3, 4, so about 400 kilometers. See, is that 4? So about 400 kilometers above the Earth's surface. This is the ISS, and you can read what the gravitational field strength is on the ISS. It's just below 9. So you can see that the weightlessness part of astronauts floating around certainly isn't anything to do with there being less gravity in space, because the drop off between Earth and space is almost insignificant. Sure, we can get something, is what we'll talk about in a second, is a geostationary satellite. Now, geostationary satellites must orbit with an altitude, with a height above the Earth of 32,000 kilometers. My graph here goes up to 14,000 kilometers. When you get all the way up to 32,000 kilometers, you'll have a gravitational field strength, and it will only be at 0.3. And so there will be a much, much smaller amount of gravity. Here's where I'm saying, where I flashed up that big, there's no gravity in space, or don't talk about there being no gravity in space. Even with a gravitational field strength of 0.3 newtons per kilogram, it's still enough to cause the satellite to move in an orbital path. The moon is a distance of 383,000 kilometers, so my graph would have to go up to 383 here. And at that point, you would have a gravitational field strength, well, you won't even be able to see it, of around about 3 millinewtons. So 3 milli, the gravitational attraction between the Earth and the moon, you have 3 millinewtons. But even that is enough to cause it to move in an orbital path. The moon orbits our Earth, but the gravitational attraction there is tiny. Okay, so even with very small gravitational fields, you're still going to be influenced by this. Okay, so what do we need to know about the altitude of satellites? If you remember back to our learning outcomes say that I know that the period of satellite in a high altitude orbit is greater than the period of a satellite in a lower altitude orbit. So we've obviously got to know something about altitude of satellites and how that affects what we would call their period. And for this we have, you don't need to know this. This is sort of a, well, it's certainly the understanding, the application of this is well beyond the scope of National 5 physics, higher physics as well, and indeed we get into this in advanced higher physics, and this is what is known as Kepler's third law. So Johann Kepler was a German astronomer. He was alive at the end of the 16th century, beginning of the 17th century, and he came up with, well, obviously you can guess, he came up with at least 3 laws of planetary motion. The first 2 we don't really need to worry about. But Kepler's third law, what it really says is, and there's, if you're a lover of all things algebra, there's a kind of nice derivation which you can do. Ask me about it if you want to see the real derivation. I'm happy to give it to you, see if you can have a wee challenge to do some algebraic manipulation of physics formulas. But it has got nothing to do with National 5 course, just be aware of that. You'll be doing some advanced higher work. So Kepler's third law, what it's basically meaning or saying is that, I'll write it out, t squared equals, or no, it is directly proportional to r cubed. T being the period of a satellite. Now, if you remember from waves, our period of our satellite is going to be the time for one complete wave, which is where you'll have heard it before, but we'll also use period for orbits. And so period is the time for one complete orbit, i.e. the time it takes to go around there. And we're saying that the period squared is directly proportional to the radius cubed. Now what we're talking about with the radius from the centre of the Earth is the distance there. And so this is the radius. And what it's saying is that that is directly proportional to that. You could paraphrase to say that period, i.e. the time it takes to go round once, is kind of the same as, or directly proportional to r. Which means if you get a bigger value of r, see r is bigger now, then t must become bigger. So if you increase the altitude, the height, it takes longer to go round. How do you do that? How do you increase the radius? Well, you increase the radius by speeding it up. Okay. There's also more formulas which we can show, which will be determined about velocity. So the velocity of the satellite. If you remember when we go back to this original bit about satellites, if you have your satellite and it's traveling just too slow to be in a stable orbit, well, it could, in theory, just break out of orbit and come crashing down. If you have it speeded up a wee bit, it wouldn't maintain this orbital path, but if you speed it up, so if you increase this horizontal velocity, what you can have is it will just go into a higher orbit. And so the orbit of the satellite with an increased horizontal velocity would look something like that. Okay, so in order to get an increased radius and therefore an increased period, you speed it up. To decrease its altitude, you slow it down. Slow a rocket down and it will go back towards the Earth. You speed a rocket up, it will move further away from Earth. But I think what we're going to do is we will leave it there for now, and I'll make this one video, and then when I come back we'll do another video that is going to be looking at getting there in the first place, getting up into space, and then going on what happens if we want to go and visit Saturn. And so space travel, interplanetary travel, and travel further afield in our solar system. And so that'll be all for now. Thanks for watching, and I'll see you again very soon. Okay, thanks. Bye.